picture this. You're standing on a beach at midnight, staring out at the ocean. The waves crash against the shore and you wonder, where does it end? Where does the water meet something else? Now, take that feeling, that curiosity, and multiply it by infinity. That's what we're dealing with when we ask, what's at the edge of the expanding universe? Here's the thing that'll blow your mind right from the start. The universe doesn't have an edge. Not in the way you're thinking. There's no cosmic wall. No, beyond this point, here be dragons' sign floating in the void. But stay with me, because what's actually happening is so much stranger, so much more profound, that it'll fundamentally change how you see reality itself. Let me take you back. 13.8 billion years ago, everything, and I mean everything, existed in a space smaller than the period at the end of this sentence. Every atom in your body, every planet, every star, every galaxy that will ever exist, compressed into an unimaginably hot, dense point. Then, in a fraction of a second so small we don't have words for it, the universe began expanding. Not exploding outward into empty space like a bomb, because there was no space to explode into. Space itself was expanding. Space itself was being created. Think about that. Space isn't just the stage where the cosmic play unfolds. Space is part of the play. It's being written as we speak. Now, when people hear the Big Bang, they often imagine a bomb going off in the middle of darkness, with matter flying outward into a pre-existing void. That's wrong. Completely wrong. The Big Bang happened everywhere simultaneously. It happened right here where you're sitting. It happened in every cubic centimeter of space in the entire universe at once. The universe wasn't expanding into something. The universe is the something, and it's getting bigger. So if there's no edge, what are we even talking about? Well, there's something we can't see, and there's a reason we can't see it. That invisible boundary, that cosmic horizon, is one of the most fascinating concepts in all of physics. It's called the observable universe, and beyond it lies the unobservable universe, a realm we will never touch or see, no matter how advanced our technology becomes. The observable universe has a radius of about 46.5 billion light-years in every direction. Wait, you might be thinking, if the universe is only 13.8 billion years old, how can we see light from 46 billion light-years away? Wouldn't light have only had time to travel 13.8 billion light-years? Here's where it gets beautiful. While that light was traveling toward us, space itself was expanding, stretching, carrying those distant objects away from us even as their light journeyed in our direction. It's like running on a treadmill that's accelerating. You're moving forward, but the destination is getting farther away. This creates something remarkable, a cosmic horizon. Just like you can't see past the horizon on Earth because of the planet's curvature, we can't see past the cosmic horizon because light from beyond it hasn't had time to reach us yet. But here's the twist, it never will. Not because it's moving too slowly, but because space between us and those distant regions is expanding faster than light can cross it. That's right, faster than light. Einstein told us nothing can move through space faster than light, and he was right. But space itself doesn't have to obey that speed limit. Space can expand at any rate it wants, and in the far reaches of the universe, it's expanding so rapidly that light emitted from those regions will never reach us. Ever. Those galaxies are being swept away from us by the tide of expanding space, and we're losing them one by one to the darkness beyond our cosmic horizon. Now, let's talk about what we can see, what lies within that horizon. When you look up at the night sky, you're not seeing the universe as it is. You're seeing the universe as it was. Light takes time to travel, so the farther away something is, the further back in time you're looking. The sun you see in the sky is 8 minutes old. The nearest star, Proxima Centauri, appears as it was 4 years ago. The Andromeda Galaxy, 2.5 million years in the past. The most distant galaxies we've observed with the James Webb Space Telescope, we're seeing them as they appeared just a few 100 million years after the Big Bang, when the universe was an infant still forming its first stars. This means when we look out into space, we're looking back through time itself. We're cosmic archaeologists, digging through layers of light, uncovering the history of everything. And the deepest layer we can see, the oldest light in the universe, is the cosmic microwave background radiation, the afterglow of the Big Bang itself, a faint whisper of radiation that fills all of space, a baby picture of the universe taken when it was just 380,000 years old. Before that moment, the universe was opaque. It was so hot and dense that light couldn't travel freely. Photons would scatter off electrons like a car trying to drive through a thick fog. But then, at 380,000 years, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, and suddenly, light was free. The fog cleared. The universe became transparent, and that first light, stretched and cooled by billions of years of expansion, is what we detect today as the cosmic microwave background. This is our horizon. Beyond it, we cannot see, not because there's nothing there, but because the light from anything beyond hasn't reached us yet. And here's the kicker. There's something even more fundamental limiting what we can ever hope to see. The universe isn't just expanding, it's accelerating. In 1998, two teams of astronomers studying distant supernovae made a discovery that shocked the world. They expected to find that the expansion of the universe was slowing down, decelerated by the gravitational pull of all the matter in the cosmos. Instead, they found the opposite. The expansion was speeding up. Galaxies weren't just moving away from us, they were moving away faster and faster. This acceleration is caused by something we call dark energy, a mysterious force that permeates all of space and pushes the universe apart. We don't know what dark energy is. We don't know where it comes from, but we know it's real and we know it's winning. Dark energy makes up about 68% of the total energy content of the universe. Dark matter, which we also don't fully understand, makes up about 27%. Everything we can see, all the stars, planets, gas clouds, you, me, everything made of atoms, makes up less than 5% of the universe. We're a cosmic footnote, living in a universe dominated by things we can't see and don't understand. Because of dark energy, there's a sphere around us, centered on Earth, beyond which galaxies are receding faster than light. This sphere is called the Hubble sphere, and it defines a special boundary in space. Galaxies beyond this boundary are moving away from us so quickly that any light they emit toward us will never reach us. They're not just invisible, they're permanently inaccessible. They exist in a part of the universe that is, for all practical purposes, separate from ours. And that sphere is shrinking. Well, not the sphere itself, but the number of galaxies within it. As the universe continues to expand and accelerate, more and more galaxies will cross that boundary and disappear from view. In the far future, trillions of years from now, the night sky will be a lonelier place. Most of the galaxies we see today will have been swept beyond the cosmic horizon, their light stretched into invisibility. Future astronomers, if they exist, will look up at a nearly empty sky and might conclude they live in a small, isolated island universe. They won't see the cosmic microwave background. They won't see distant galaxies. They'll have no evidence of the Big Bang. The universe will have erased its own history. We're living in a special time, a cosmic golden age, where we can still see the evidence of our origins. We can still observe the deep history of the universe. In a sense, we're lucky to exist now, when the universe is still young enough to show us its secrets. But let's get back to the edge. If the universe is infinite, as many physicists suspect, then there is no edge. Infinity has no boundary. You could travel in a straight line forever and never reach the end. But if the universe is finite, shaped perhaps like the surface of a sphere, a three-dimensional surface curved through higher dimensions, then you could, in theory, travel in a straight line and eventually return to where you started, like Magellan circumnavigating the Earth. We don't know which it is. Our observations suggest the universe is flat or very nearly flat, which could mean it's infinite. But we can only measure the curvature within the observable universe. Beyond our horizon, space could curve in ways we can't detect. The true shape of the universe, its ultimate geometry, remains one of cosmology's great unsolved mysteries. Here's another mind-bending possibility. What if our universe isn't the only one? What if, beyond the edge of our observable universe, beyond even the unobservable parts of our universe, there are other universes, each with its own laws of physics, its own constants of nature, its own history? This is the multiverse hypothesis, and while it sounds like science fiction, it emerges naturally from some of our best theories. Eternal inflation, a refinement of the Big Bang theory, suggests that the rapid expansion that started our universe, inflation, never completely stopped. In tiny patches, inflation ends and a universe like ours forms. But in the vast majority of space, inflation continues forever, spawning an infinite number of bubble universes, each causally disconnected from the others. If this is true, then asking what's at the edge of the universe is like asking what's at the edge of Earth's surface? The question doesn't make sense because there is no edge. But there are other patches, other regions, eternally beyond our reach. Our universe would be one bubble in an infinite foam of universes, each one a separate reality, and we'd never be able to prove whether any of them exist. But let's bring it back to what we can observe, what we can study. Within our observable universe, we've mapped the large-scale structure of the cosmos. Galaxies aren't scattered randomly through space. They're organized into an intricate cosmic web, with vast filaments and walls of galaxies separated by enormous voids where almost nothing exists. These structures formed from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years into the cosmic architecture we see today. The largest structures we've found are mind-bogglingly huge. The Hercules Corona Borealis Great Wall is a galactic superstructure stretching across 10 billion light-years, about 1/8 the diameter of the observable universe. It's so large that light takes 10 billion years just to cross it. Structures this big challenge our understanding of how the universe evolved. According to our models, there shouldn't be enough time since the Big Bang for gravity to have assembled something so massive. Yet there it is. The universe doesn't care about our models. As we peer deeper into space, as we develop more powerful telescopes and more sophisticated instruments, we're pushing the boundaries of the observable universe. The James Webb Space Telescope, launched in December 2021, has been breaking records, observing galaxies that formed just a few hundred million years after the Big Bang. These early galaxies look different from modern ones. Smaller, more chaotic, blazing with the light of massive young stars. They're cosmic teenagers, and studying them helps us understand how galaxies grew up, how they evolved into the majestic spirals and ellipticals we see in the nearby universe. But Webb is just one tool in our cosmic toolkit. The Event Horizon Telescope gave us our first image of a black hole's shadow. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected ripples in spacetime from colliding black holes and neutron stars. The Square Kilometer Array, currently under construction, will be the world's most powerful radio telescope, capable of mapping hydrogen gas across cosmic history and probing the dark ages of the universe, that mysterious era between the cosmic microwave background and the formation of the first stars. Each new instrument, each new observation, pushes our horizon a little farther, reveals a little more of the universe's secrets. And every answer we find raises 10 new questions. Consider dark matter. We know it's there because we can see its gravitational effects. Galaxies rotate too fast to be held together by the gravity of their visible matter alone. Galaxy clusters bend light from background objects more than they should based on the mass we can see. The cosmic microwave background has patterns that require dark matter to explain. Yet we've never detected a dark matter particle. We don't know what it's made of. Could be exotic particles left over from the Big Bang, WIMPs, axions, or something we haven't even imagined yet. Or it could be something even stranger, a sign that our theory of gravity itself needs modification. Then there's dark energy. At least with dark matter, we have candidates, particles we can look for. Dark energy is more mysterious. It could be the energy of empty space itself, a property inherent to the vacuum. Quantum mechanics predicts that even empty space should have energy, But when we calculate how much, we get an answer that's off by a factor of 10 to the power of 120. That's not just wrong. It's spectacularly, embarrassingly wrong. It's the worst prediction in the history of physics. Yet something is accelerating the universe's expansion, and we're calling it dark energy because we have no idea what else to call it. Maybe dark energy isn't constant. Maybe it's changing over time, evolving as the universe ages. Maybe it will grow stronger, eventually tearing apart galaxies, stars, planets, atoms, even space and time itself in a catastrophic big rip. Or maybe it will weaken, allowing gravity to take over and reverse the expansion in a big crunch. Or maybe, just maybe, it will stay perfectly balanced, and the universe will expand forever, cooling and darkening until all the stars burn out and the cosmos becomes a cold, empty void, the heat death of the universe. The fate of the universe hangs on the nature of dark energy, and we don't know what that nature is. But let's zoom out even further. Let's think about the universe not just in space, but in time. The universe has a history, a life story, and we're living in one chapter of that story. In the beginning, there was the Big Bang, or more accurately, the inflationary epoch, when the universe expanded faster than light, smoothing out irregularities and setting the stage for everything that came after. Then came the radiation era, when the universe was dominated by light and other forms of electromagnetic radiation, too hot for atoms to exist. As the universe expanded and cooled, matter took over, and gravity began sculpting the cosmic web. The first stars ignited, then the first galaxies formed, and for billions of years, the universe was a bustling, thriving place, filled with light and energy. We're currently in what you might call the stelliferous era, the age of stars. But this era won't last forever. Stars are born from clouds of gas, and as they burn, they convert hydrogen into heavier elements. Eventually, the universe will run out of hydrogen, and star formation will cease. The last stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. The universe will grow dark, but even that's not the end. Black holes, as massive and eternal as they seem, aren't permanent. Stephen Hawking showed that black holes emit radiation and slowly evaporate. It takes an incomprehensibly long time, 10 to the power of 100 years for a black hole with the mass of the sun, but eventually even black holes will disappear. What's left will be a thin soup of particles, spread across an ever-expanding, ever-cooling universe. Protons themselves might decay, given enough time, leaving nothing but photons and other stable particles drifting through the void. This is the heat death, the final equilibrium, a state of maximum entropy where nothing happens because nothing can happen. The universe reaches a state where no more energy can be extracted, no more work can be done. Time loses meaning when nothing changes. But here's a thought that might give you some comfort. That's trillions upon trillions upon trillions of years in the future. Right now, we're in the prime of the universe's life, the era when the most interesting things are happening. Stars are shining, galaxies are colliding, black holes are feeding, planets are forming, life exists. Consciousness has emerged from the chaos to contemplate the cosmos itself. We're not just observers of the universe, we're the universe observing itself. And that brings us to perhaps the most profound question of all. Are we alone? In this vast, expanding universe with its hundreds of billions of galaxies, each containing hundreds of billions of stars, is Earth the only place where life exists, where intelligence has emerged, where a species has looked up at the sky and asked, "What's out there?" The odds seem stacked against us being alone. The ingredients for life, carbon, hydrogen, oxygen, nitrogen, are among the most common elements in the universe. We've found planets around other stars, thousands of them, including many in the habitable zones where liquid water could exist. We've found organic molecules in space, in asteroids, in comets, in the atmospheres of distant moons. The building blocks of life are everywhere. Yet we haven't found life anywhere but Earth. Not yet. The Fermi paradox asks, if life is common, where is everybody? Why haven't we detected signals from alien civilizations? Why hasn't someone visited us? Are we really the first? Or is there something preventing civilizations from spreading across the galaxy? Some great filter, some obstacle that destroys intelligent species before they can reach the stars? Maybe the great filter is behind us. Maybe the emergence of life or the evolution of intelligence or the development of technology is so improbable that we're the first to make it this far. If that's true, we have a responsibility, a cosmic responsibility to survive, to spread, to ensure that intelligence and consciousness persist in the universe. Or maybe the great filter is ahead of us. Maybe every civilization reaches a point where it destroys itself through war or environmental collapse or some technology we haven't imagined yet. Maybe that's why the universe is silent. Maybe the skies are filled with the ruins of dead civilizations, each one a warning we can't hear. We don't know, but the search continues. SETI, the search for extraterrestrial intelligence, scans the skies for signals. The Breakthrough Listen project uses some of the world's most powerful telescopes to survey 1 million nearby stars. The James Webb Telescope analyzes the atmospheres of exoplanets, looking for biosignatures, oxygen, methane, other gases that might indicate the presence of life. If we find it, if we detect a signal or discover microbes on Mars or see signs of life in the clouds of Venus, it will be the most important discovery in human history. It will answer a question we've been asking since we first looked up at the stars. Are we alone? And the answer will change everything. But even if we are alone, even if Earth is the only oasis of life in a vast cosmic desert, that makes us precious. It makes every human being, every living thing, every blade of grass, every bacterium part of a rare and beautiful experiment. We're the universe waking up, becoming aware of itself. We're stardust contemplating the stars. Now, let's get back to the edge, the boundary, the horizon. We've talked about the observable universe, the cosmic microwave background, the limits of what we can see. But there's another kind of edge, a physical boundary not in space, but at the boundary between space and something else. Black holes. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. At the center is a singularity, a point where the curvature of space-time becomes infinite, where our equations break down and physics as we know it ceases to function. Surrounding the singularity is the event horizon, the point of no return. Cross that boundary and you're done. You're falling inward, and no force in the universe can save you. The event horizon is an edge, a true boundary in space-time. But here's what's weird. From the outside, you can't tell what's beyond it. You can't see through it. Information that crosses the event horizon is lost to the outside universe forever. This creates a paradox because quantum mechanics says information can never be truly destroyed. So where does it go? Does it somehow remain encoded on the surface of the event horizon? Does it leak out through Hawking radiation? Or is information actually destroyed, forcing us to rewrite the laws of physics? This is the black hole information paradox, and it's been a thorn in the side of theoretical physics for decades. It suggests that our understanding of space-time, gravity, and quantum mechanics is incomplete. There's something deeper, some underlying principle we haven't grasped yet. Maybe the answer lies in quantum gravity, a theory that unifies general relativity and quantum mechanics. String theory, loop quantum gravity, other approaches are all attempting to bridge this gap. They suggest that space-time itself isn't fundamental, that at the smallest scales, space and time emerge from something more basic, a quantum foam, a network of relationships, a hologram projected from a lower dimensional boundary. If space-time isn't fundamental, then asking what's at the edge of the universe is like asking what's north of the North Pole. The question doesn't make sense within the framework of the theory. The universe doesn't have an edge because the concept of edge requires space-time, and space-time is something that exists within the universe, not outside it. This might sound like philosophical hand-waving, but it's based on real physics, real mathematics, real attempts to understand the deepest nature of reality. And it leads to some truly wild ideas. Consider the holographic principle. This idea, which emerged from the study of black holes, suggests that all the information contained in a volume of space can be encoded on the boundary of that space, like a hologram. Your body, your thoughts, your entire three-dimensional existence might be encoded on a two-dimensional surface at the edge of the universe. You're a projection, a shadow cast by information living on a distant boundary. It sounds crazy, but it's taken seriously by many physicists because it solves certain problems in quantum gravity. And it raises a disturbing possibility. Maybe our entire universe, everything we experience, is a simulation running on a two-dimensional substrate. Maybe reality itself is an illusion, a very convincing one, but an illusion nonetheless. Or consider the many worlds interpretation of quantum mechanics. In this view, every time a quantum event occurs, every time a particle could go left or right, spin up or spin down, the universe splits into multiple branches, each one representing a different outcome. You exist in all these branches simultaneously, a vast tree of possibilities spreading across the multiverse. In this interpretation, there's no single edge to the universe because there's no single universe. There's a vast landscape of parallel realities. Each one is real as the others, and you're living in all of them. These ideas push the boundaries of what we can understand, what we can test, what we can even conceive of. They take us to the very edge of physics, to the frontier where science meets philosophy, where mathematics meets metaphysics. And they remind us of a humbling truth. The more we learn about the universe, the more we realize how much we don't know. Every answer opens new questions. Every discovery reveals new mysteries. The edge of our knowledge is always receding, always just beyond our grasp. And that's not a flaw, that's the beauty of science. That's the adventure. Let's talk about time for a moment, because when we discuss the edge of the universe, we're not just talking about space. We're talking about space-time, the four-dimensional fabric that Einstein revealed to us. Space and time are intertwined, inseparable. You can't talk about one without the other. What does it mean to reach the edge of time? Well, we know there's a beginning, the Big Bang, the moment when time itself started. But is there an end? Will time go on forever? Or will it eventually stop? The answer depends on the fate of the universe. If the universe expands forever, cooling and darkening, then time might continue indefinitely. But as the universe approaches maximum entropy, as it reaches the heat death, time becomes less meaningful. When nothing changes, when there are no more events to mark the passage of moments, does time still exist? It's a question that has puzzled philosophers and physicists alike. Time might persist mathematically, but it loses its physical significance. It becomes an empty parameter in the equations, a coordinate with no observable consequence. On the other hand, if the universe eventually stops expanding and begins contracting, if gravity wins out and pulls everything back together in a big crunch, then time might end in a singularity, a mirror image of the Big Bang. Space and time would collapse back into an infinitely dense point, and everything, all of history, all of existence, would be compressed back into nothingness. The universe would end, and time would cease. But even that might not be the end. Some cosmologists have proposed cyclic models, where the universe undergoes an infinite series of expansions and contractions, big bangs followed by big crunches followed by new big bangs. Each cycle might have different laws of physics, different constants, different outcomes. We'd be living in one cycle among infinitely many, and the edge of our universe would simply be the transition to the next cycle. There's also the possibility of a big rip, where dark energy grows so strong that it tears apart the fabric of spacetime itself. First, galaxies would be ripped apart, then stars, then planets, then atoms, then even the vacuum of space. At the moment of the big rip, the expansion rate becomes infinite, and spacetime itself is destroyed. Time doesn't just end. It's shredded, annihilated, erased from existence. Any of these scenarios could be our fate. We don't know which one is correct because we don't understand the nature of dark energy. We're fumbling in the dark, making educated guesses based on limited data. And that's okay. That's the nature of science at the cutting edge. We're explorers venturing into unknown territory, and sometimes we're wrong. Sometimes we take a wrong turn. But we learn, we adapt, we refine our theories, and we keep pushing forward. Speaking of pushing forward, let's talk about the future of cosmology. The tools and techniques that will help us explore even deeper into the cosmos and closer to the edge of the observable universe. The James Webb Space Telescope is just the beginning. Next-generation telescopes, both in space and on the ground, are being planned and built. The Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will survey the sky in infrared light, studying dark energy, exoplanets, and the structure of the galaxy. The extremely large telescope under construction in Chile will have a primary mirror 40 meters across, large enough to see the atmospheres of exoplanets in unprecedented detail. The square-kilometer array will map the distribution of hydrogen gas across cosmic history, revealing how galaxies formed and evolved. And then there's the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave detector that will observe ripples in spacetime from supermassive black hole mergers, from binary star systems, from the echoes of the Big Bang itself. Gravitational waves pass through matter without being absorbed or scattered, which means they carry information from the earliest moments of the universe, long before the cosmic microwave background was released. If we can detect primordial gravitational waves, we could peer back to the inflationary epoch, just a fraction of a second after the Big Bang, when the universe was expanding faster than light. We could test theories of quantum gravity, probe energies far beyond what any particle accelerator can reach, and answer fundamental questions about the origin of everything. But there are limits to what telescopes can show us. There are horizons we can't cross, boundaries we can't breach. The cosmic microwave background is a wall we can't see through because the universe was opaque before it. We can never observe anything earlier than 380,000 years after the Big Bang with electromagnetic radiation. To go further back, we need gravitational waves, neutrinos, or some form of radiation we haven't discovered yet. And even with all our technology, even with telescopes spanning continents and detectors stretching across the solar system, we'll never see beyond the cosmic horizon, never observe the galaxies being swept away by the accelerating expansion. We'll never know if the universe is truly infinite or merely very large. We'll never confirm whether the multiverse exists or if we're alone in a single cosmos. These are the limits of observation, the boundaries imposed by the speed of light and the expansion of space. But they're not the limits of understanding. We can still construct theories, build models, do the mathematics, and see where the equations lead us. We can extrapolate from what we know and make predictions about what lies beyond. We can use our minds to travel where our telescopes cannot. And that's the power of human intellect, the triumph of science and reason. We're bound to this tiny planet in a vast universe, limited by the speed of light and the short span of our lives. Yet we've figured out the age of the cosmos, the composition of stars, the history of galaxies, the fate of the universe. We've decoded the language of reality, written in mathematics and tested through experiment. We've pushed the boundaries of knowledge to the very edge of the observable and beyond into realms of pure thought and imagination. Think about what we've accomplished. A few centuries ago, we believed the Earth was the center of the universe, that the stars were fixed on a celestial sphere, that the cosmos was eternal and unchanging. Now we know we're on a planet orbiting an average star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies, expanding from a hot, dense state 13.8 billion years ago and accelerating toward a cold, dark future trillions of years hence. We've discovered quantum mechanics and relativity. We've split the atom and detected gravitational waves. We've sent spacecraft to every planet in our solar system and rovers to Mars. We've landed humans on the moon and built telescopes that can see to the edge of the observable universe. In the span of a few human lifetimes, we've transformed our understanding of reality itself. And we're not done, not even close. The next few decades will bring discoveries we can't even imagine. We'll find exoplanets with signs of life. We'll detect dark matter particles. We'll probe the nature of dark energy. We'll test quantum gravity at the edge of black holes. We'll map the cosmic web in exquisite detail and watch galaxies form in real time, or at least in the delayed time of ancient light reaching our instruments. We'll push the boundaries of the observable universe, and we'll learn whether we're living in an infinite cosmos or a finite but unbounded space. We'll discover whether our universe is one of many in a vast multiverse or the only reality that exists. We'll answer questions we've been asking for millennia and uncover new mysteries we never knew existed. But perhaps the most important discoveries won't be about the universe out there. They'll be about the universe in here within us. Because we're not separate from the cosmos, we're part of it. The atoms in your body were forged in the hearts of stars. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of it was created in stellar furnaces and scattered across the galaxy by supernova explosions. You're made of stardust, literally, and the energy flowing through your cells, powering your thoughts and movements, can be traced back to the Big Bang. The warmth of your body is a direct descendant of the primordial heat that filled the universe billions of years ago. You're a living, breathing embodiment of cosmic history, a temporary arrangement of matter and energy that has become aware of its own existence. Consciousness is perhaps the greatest mystery of all. How does the universe become aware of itself? How do atoms, governed by the simple laws of physics, arrange themselves into brains that can think, feel, wonder, and create? How does matter give rise to mind? We don't know. Neuroscience has made incredible progress, mapping the brain, identifying the neural correlates of consciousness, understanding how information is processed and stored. But the hard problem remains: why does it feel like something to be you? Why is there subjective experience? Why does the universe have an inner life? Some philosophers and scientists have suggested that consciousness might be fundamental, woven into the fabric of reality itself. Others argue it's an emergent property, arising from complexity but not reducible to it. Still others propose that consciousness is an illusion, a trick the brain plays on itself. We don't have answers, only speculations and theories waiting to be tested. But here's what we do know: consciousness exists. You exist. You're experiencing this moment, this thought, this cascade of ideas flowing through your mind. And that's miraculous. Against all odds, against the vast emptiness and indifference of the cosmos, you're here. You're alive. You're thinking. You're wondering about the edge of the universe, about the nature of reality, about your place in the grand scheme of things. And here's the thing: your place is significant. Not because the universe cares about you, it's not conscious, but because you care. Because you can find meaning, create beauty, love and be loved, learn and teach, build and discover. You're a way for the universe to know itself, to explore itself, to marvel at its own existence. In a very real sense, you're the universe looking back at its origin, contemplating its fate, asking what lies beyond the edge. The question isn't just, what's at the edge of the universe? It's, what are we? And how did we come to ask this question? And that question is just as profound, just as deserving of exploration. So when you look up at the night sky, when you see the stars and planets and the faint glow of the Milky Way stretching across the darkness, remember, you're looking at family. Those stars are your ancestors. They died so you could exist. Their deaths seeded the galaxy with heavy elements, the ingredients for planets and life. Every atom in your body has a story, a cosmic journey spanning billions of years. The oxygen you breathe was made in a massive star that exploded long before the Earth formed. The carbon in your DNA was synthesized in the core of a red giant. The gold in your jewelry was created in the collision of two neutron stars, a cataclysmic event that rippled space-time and scattered precious metals across the cosmos. You're a living testament to the creative power of the universe, a unique and temporary configuration of matter that will never exist again in quite the same way. And yet, despite being made of common elements following ordinary physical laws, you're capable of extraordinary things. You can write poetry and compose symphonies. You can discover the laws of nature and cure diseases. You can create art and build civilizations. You can love, laugh, dream, and hope. You can look up at the vastness of space and feel small, yet also significant, knowing that you're part of something far greater than yourself. That's the paradox of being human. We're insignificant specks in an incomprehensibly large universe, yet we're also the most complex structures we know of, capable of understanding that very universe. We're both nothing and everything, cosmic dust that dreams of immortality, atoms that contemplate infinity. As we push toward the edge of the universe, as we probe deeper into space and further back in time, we're not just exploring the cosmos. We're exploring ourselves. We're learning where we came from, how we got here, and where we might be going. We're part of a story that began 13.8 billion years ago and will continue for trillions of years into the future. A story of matter and energy evolving from simplicity to complexity, from uniformity to diversity, from the smooth sameness of the early universe to the rich tapestry of galaxies, stars, planets, and life. And perhaps life is the universe's way of fighting back against entropy, against the inevitable slide toward disorder and darkness. Life creates order, builds structures, concentrates energy, and fights against the cosmic tide pulling everything apart. We're local pockets of decreasing entropy in an expanding, cooling universe. We're temporary, yes, but while we exist, we matter. We make a difference. We light up the darkness, if only for a moment. So what's at the edge of the expanding universe? Maybe there's no edge. Maybe the universe is infinite, stretching forever in all directions, with no boundary, no wall, no end. Or maybe it's finite but unbounded, like the surface of a sphere, where you can travel forever without ever reaching an edge. Or maybe there's a multiverse, an infinite collection of separate universes, each with its own laws and constants, and our universe is just one bubble in an endless foam. We don't know. We may never know. But we keep looking, keep questioning, keep pushing the boundaries of what's possible. Because that's what humans do. That's what consciousness does. We refuse to accept limits. We refuse to stop wondering. We look at the universe and ask, what else is out there? What secrets are waiting to be discovered? What mysteries lie beyond the horizon? And even if we never find all the answers, even if some questions remain forever beyond our reach, the search itself is worthwhile. The journey matters as much as the destination. Every discovery, every insight, every moment of understanding brings us closer to grasping the true nature of reality. And along the way, we create meaning, we build knowledge, we connect with each other and with the cosmos itself. We're the universe waking up, opening its eyes, and seeing itself for the first time. We're the part of the cosmos that asks questions, that seeks answers, that refuses to accept ignorance and darkness. We're explorers standing on the shore of the cosmic ocean, peering out at the vast unknown, and daring to wonder what lies beyond the horizon. And that, ultimately, is what's at the edge of the expanding universe. Not a wall or a boundary or an end, but a question, an invitation, a challenge to keep exploring, keep discovering, keep pushing forward into the unknown. The edge isn't a place you reach. It's a frontier that moves with you, always receding, always beckoning you onward. Because in the end, the universe is less about what it is and more about what we make of it. It's a canvas for our curiosity, a playground for our intellect, a mirror reflecting our deepest questions back at us. The edge of the universe is wherever we dare to look next, whatever question we dare to ask. And as long as we keep asking, keep exploring, keep wondering, the universe will keep revealing its secrets, one discovery at a time. We stand at a unique moment in cosmic history. The universe is old enough that we can see its deep past, young enough that we can still observe distant galaxies before they slip beyond the horizon. We have the tools to probe the cosmic microwave background, detect gravitational waves, and study exoplanets. We have the knowledge to understand what we're seeing and the imagination to ask what it all means. Future generations, if they exist, will envy us. They'll wish they could have lived in this era, when the universe still bore the scars of its birth, when the cosmic web was still visible, when there was still so much to discover. We're cosmologists living in a golden age, astrophysicists witnessing the universe's prime, conscious beings lucky enough to exist when existence is still interesting. So look up, marvel at the night sky, think about the photons entering your eyes, particles of light that have traveled for years or centuries or millions of years to reach you. Think about the stars that made you, the supernovae that seeded the galaxy with the elements of life. Think about the vast stretches of space between galaxies, the dark matter holding everything together, the dark energy pushing everything apart. Think about the edge of the observable universe, 46 billion light-years away in every direction, a sphere of visibility centered on you, on Earth, on this moment in time. Beyond that edge, the universe continues, perhaps forever, perhaps looping back on itself, perhaps giving way to other universes in an infinite multiverse. We don't know, but we can imagine, we can calculate, we can theorize, we can explore with our minds what we cannot reach with our telescopes. And maybe that's enough. Maybe the question is more important than the answer. Maybe the wonder we feel when contemplating the cosmos is the point, the purpose, the meaning we've been looking for all along. We're the universe experiencing wonder at itself. We're existence becoming aware of its own mystery. The edge of the expanding universe isn't out there in space. It's here in this moment in your mind, in the questions you ask and the thoughts you think. Every time you wonder about the cosmos, you're exploring the edge. Every time you learn something new, you push that edge a little farther. The universe expands, and so does your understanding, and in a very real way, those two expansions are connected. We're made of the universe, and the universe is known through us. The atoms in your brain are contemplating the atoms in distant galaxies. The energy flowing through your neurons is kin to the energy flooding through space. You're not separate from the cosmos. You're a part of it, as much as any star or planet or black hole. And when you think about the universe, when you marvel at its size and age and beauty, you're participating in a grand cosmic awakening, a process that began with the Big Bang and continues through us, through every conscious mind that looks up and wonders. So what's at the edge of the expanding universe? Maybe the answer is us, our curiosity, our questions, our never-ending desire to know, to understand, to explore. The edge isn't a place, it's a state of mind. It's the boundary between what we know and what we don't, between the familiar and the unknown, between the light of understanding and the darkness of mystery. And as long as there are questions to ask and mysteries to solve, as long as there's a universe to explore and minds to explore it, that edge will always be there, calling to us, inviting us to venture one step further into the unknown. The universe is vast beyond measure, ancient beyond comprehension, complex beyond imagination. It's expanding, accelerating, evolving from simplicity to complexity and back to simplicity again. It's filled with dark matter we can't see, dark energy we don't understand, and mysteries we haven't even discovered yet. But it's also filled with light, with stars illuminating the darkness, with galaxies swirling in cosmic dances, with planets orbiting quietly in their habitable zones, perhaps teeming with life, with conscious beings like us, looking up at the sky and asking the biggest questions imaginable. We're here, now, in this moment, on this planet, in this universe. We're temporary arrangements of matter and energy, brief flickers of consciousness in an incomprehensibly vast cosmos. But while we exist, we matter. We create meaning. We build knowledge. We explore the universe and share what we learn with each other, generation after generation, building on the discoveries of those who came before us and laying the groundwork for those who will come after. That's our legacy. That's our gift to the future. Not just the knowledge we accumulate, but the curiosity that drives us to seek it. The sense of wonder that makes us look up at the stars and ask, what's out there? How does it work? Where did it come from? Where is it going? These questions connect us across time and space, across cultures and languages, across all the barriers that divide us. We're all humans, all conscious beings, all participants in the grand cosmic story. We're all stardust, all relatives, all children of the universe. And when we look out at the expanding cosmos, when we contemplate the edge of the observable universe and wonder what lies beyond, we're doing something profoundly human. We're refusing to accept limits. We're pushing boundaries. We're exploring not just space, but the limits of understanding itself. That's what makes us special. Not our place in the universe, we're nowhere special, just one planet among trillions. But our ability to ask questions, to seek answers, to look at the vast, indifferent cosmos and find meaning, beauty, and wonder. That's our superpower. That's what makes us matter, even in a universe that doesn't care whether we exist or not. So keep asking questions, keep looking up, keep wondering about the edge of the universe and what lies beyond. Because every question you ask, every thought you think, every moment of wonder you experience is a victory against the darkness. It's a declaration that consciousness exists, that meaning can be found, that the universe is not just a collection of particles obeying mindless laws, but something more, something capable of knowing itself, of understanding itself, of marveling at its own existence. You are that something. You are the universe's way of comprehending itself. You are stardust that learned to think, atoms that became aware, matter that developed a mind. You are the cosmos waking from a dreamless sleep and asking, for the first time, what am I? Where did I come from? What happens next? Those questions don't have final answers. The universe is too vast, too complex, too mysterious for any finite mind to fully comprehend. But that's okay. That's beautiful, because it means there will always be more to discover, always another horizon to reach, always another edge to explore. The expanding universe isn't running away from us. It's inviting us to chase it, to push our understanding further, to never stop exploring, never stop questioning, never stop wondering. And as long as there are humans or any conscious beings to accept that invitation, the universe will continue to reveal its secrets, one marvel at a time. So here we are, standing on this tiny world, looking out at infinity and asking what's at the edge. The honest answer is we don't know. We may never know, but we're going to keep looking, keep thinking, keep exploring, because that's what we do. That's who we are. We're explorers. We're questioners. We're the universe's way of knowing itself. And that, more than any specific discovery or theory or answer, is what truly lies at the edge of the expanding universe. Now let's dig deeper into something that'll really bend your brain. When astronomers measure the expansion of the universe, they're not watching galaxies move through space like cars on a highway. They're watching space itself stretch. Imagine you're an ant on the surface of a balloon and someone's inflating it. You're not walking anywhere, but suddenly the ant on the other side of the balloon is getting farther away. That's what's happening to galaxies. They're not racing away from us. They're standing still while the space between us expands. Here's where it gets wild. Edwin Hubble, back in 1929, discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship, distance versus velocity, is now called Hubble's law. But Hubble didn't know he was measuring the expansion of space itself. He thought he was just seeing galaxies moving through a static universe. It took years for physicists to fully grasp what he'd actually discovered. The universe is growing, and it's been growing since the Big Bang. The rate of expansion is described by something called the Hubble constant, except it's not actually constant. It changes over time as the universe evolves. Right now, the Hubble constant is about 70 kilometers per second per megaparsec. What does that mean? For every million parsecs, about 3.3 million light-years of distance between us and a galaxy, that galaxy appears to be receding at 70 kilometers per second faster. A galaxy 10 million parsecs away is receding at 700 kilometers per second. A galaxy 100 million parsecs away 7,000 kilometers per second. Do the math far enough out, and you'll find galaxies receding faster than the speed of light. Not because they're violating Einstein's speed limit, but because the space between us is expanding faster than light can cross it. These galaxies exist in what we call the unobservable universe, and we will never, ever see them. They're gone, lost to the accelerating expansion, as unreachable as if they existed in another dimension. But here's what keeps cosmologists up at night. When we measure the Hubble constant using different methods, we get different answers. When we look at the cosmic microwave background and calculate what the expansion rate should be, we get 67 kilometers per second per megaparsec. When we measure it directly using nearby supernovae and Cepheid variable stars, we get 73. That's a significant discrepancy, and it shouldn't be there. Both methods are reliable. Both have been checked and rechecked. Yet they disagree. This is called the Hubble tension, and it's one of the biggest unsolved problems in cosmology. It might mean our understanding of dark energy is wrong. It might mean there's new physics we haven't discovered yet. It might mean the universe is more complicated than we thought. Maybe the expansion rate isn't the same in all directions. Maybe dark energy is evolving. Maybe there are local variations in spacetime we haven't accounted for. Or maybe, just maybe, one of our measurement methods has a systematic error we haven't found yet. But physicists have been looking for years, and they haven't found it. The tension remains, a crack in our cosmological model, a hint that something profound is waiting to be discovered. Let's talk about what happens when you try to measure distances in the universe. It's harder than you might think. You can't just point a ruler at a distant galaxy and read off the answer. Light takes time to travel, and during that journey, the universe expands. So the distance to a galaxy when it emitted the light we're seeing now is different from the distance to that same galaxy right now. Cosmologists use something called redshift to measure how much the universe has expanded since the light was emitted. Redshift works like this. When a light source moves away from you, its wavelength stretches, shifting toward the red end of the spectrum. The faster it's moving, the more it shifts. In an expanding universe, light from distant galaxies gets stretched as it travels through expanding space. By measuring how much the light has shifted, we can calculate how much the universe has expanded since that light began its journey. A galaxy with a redshift of 1 has its light stretched by a factor of 2. The universe has doubled in size since that light was emitted. A galaxy with a redshift of 2, the universe has tripled. The most distant galaxy ever observed, as of 2024, has a redshift of about 14. We're seeing it as it appeared just 280 million years after the Big Bang, when the universe was only 2% of its current age. That galaxy is a cosmic infant, and its light has been traveling toward us for over 13 billion years. But here's the kicker. That galaxy isn't 13 billion light-years away. Because the universe has been expanding while the light traveled, that galaxy is now about 30 billion light-years from us. We're seeing where it was, not where it is. By now, it's evolved into something completely different. Maybe a massive elliptical galaxy, maybe it's merged with other galaxies, maybe it's even disappeared into a supermassive black hole. We'll never know, because we're only seeing its ancient light, a photograph from the dawn of time. This creates a strange situation. The farther away we look, the further back in time we see, but also the less accurately we know where things actually are right now. The edge of the observable universe represents not just a spatial boundary, but a temporal one. We're looking at the universe as it was nearly 14 billion years ago, seeing galaxies that may not even exist anymore in their current form. Consider the Hubble Ultra Deep Field, one of the most famous astronomical images ever taken. In 2003 and 2004, the Hubble Space Telescope pointed at a tiny patch of apparently empty sky, a region about 1/10 the diameter of the full moon, and stared at it for over 11 days. When the images were combined, that empty patch revealed about 10,000 galaxies, each one containing billions of stars. Some of those galaxies are so distant, their light has been traveling for over 13 billion years. That image is a time machine. The galaxies in the foreground are relatively nearby, showing the universe as it was a few billion years ago. The galaxies in the middle distance are further back, 5 or 6 billion years ago. And the faintest, reddest galaxies in the deepest parts of the image, they're showing us the universe as it appeared in its infancy, when galaxies were just beginning to form. The James Webb Space Telescope has gone even deeper. Webb's infrared vision can see through cosmic dust and detect the light from the very first galaxies, the ones that formed when the universe was less than 500 million years old. These galaxies look strange. They're smaller, more irregular, blazing with the light of massive stars that burned fast and died young. They're cosmic pioneers, the first structures to condense out of the primordial gas that filled the early universe. Webb has found galaxies that shouldn't exist according to our models. Massive galaxies that form too early, too fast, challenging our understanding of how galaxies grow. Supermassive black holes that appeared when the universe was barely a billion years old, with masses equivalent to millions or billions of suns. How did they get so big so fast? We don't know. Our theories predict it should take longer for black holes to accumulate that much mass. Yet there they are, staring back at us from the cosmic dawn, daring us to explain them. Every time we build a more powerful telescope, we find things that surprise us. The universe refuses to fit neatly into our models. It's more complex, more dynamic, more interesting than we expected. And that's thrilling, because it means there's still so much to learn, so many mysteries waiting to be solved. Let's shift gears and talk about something that sounds like science fiction but is absolutely real: cosmic inflation. In the first fraction of a second after the Big Bang, we're talking about 10 to the negative 35 seconds, the universe underwent a period of exponential expansion. Space inflated faster than light, growing from smaller than an atom to potentially larger than the observable universe today. This all happened in less time than it takes light to cross a proton. Inflation solves several problems in cosmology. It explains why the universe is so uniform. Regions that are now on opposite sides of the observable universe were once close enough to equalize their temperature and density before inflation separated them. It explains why the universe appears flat. Any curvature would have been stretched smooth by the rapid expansion. And it explains the tiny density fluctuations we see in the cosmic microwave background, the seeds that eventually grew into galaxies and clusters. But here's what's truly mind-blowing about inflation. It might still be happening. Not here, not in our observable universe, but out beyond our horizon. The theory of eternal inflation suggests that while inflation ended in our region, creating the universe we inhabit, it continues forever in other regions, constantly spawning new bubble universes. Our universe would be just one bubble in an infinite foam, one quantum fluctuation in an eternally inflating multiverse. If eternal inflation is correct, then asking what's at the edge of the universe is like asking what's at the edge of the ocean. When you're standing on one island in an infinite sea, there are other islands out there, other bubble universes, each potentially with different laws of physics, different constants of nature, different outcomes. Some might be teeming with life. Others might be empty, inhospitable, governed by physics that doesn't allow stars or planets or atoms to form. We'd never know because we can't see them, can't reach them, can't communicate with them in any way. This leads to a controversial idea: the anthropic principle. If there are infinite universes with random physical constants, then it's not surprising that we find ourselves in one where the constants are just right for life. We couldn't exist in the others, so of course we're here. The universe appears fine-tuned for life not because it was designed that way, but because we're asking the question from the only kind of universe where observers can exist. Some physicists hate this idea. It feels like giving up, like saying the universe is this way because if it weren't, we wouldn't be here to ask. It's not falsifiable, you can't test it because you can't observe other universes. But other physicists find it compelling, even inevitable, if eternal inflation is real. The debate continues, and it gets at fundamental questions about the nature of scientific explanation. How do we make sense of a universe that might be just one random sample from an infinite ensemble? Let's ground ourselves with something more concrete. the large-scale structure of the universe. When you map the positions of galaxies across huge volumes of space, a pattern emerges. Galaxies aren't scattered randomly. They form a cosmic web, vast filaments and sheets separated by enormous voids where almost nothing exists. It looks like a three-dimensional spider web or the structure of brain cells or the foam in a glass of beer. This structure formed from gravitational amplification of tiny quantum fluctuations in the early universe. The voids are the largest structures in the universe, empty regions spanning hundreds of millions of light-years with very few galaxies inside. The Boötes void, discovered in 1981, is about 330 million light-years across, containing only a few dozen galaxies where we'd expect to find thousands. It's been called the Great Nothing, a cosmic desert, a hole in the universe. But it's not truly empty. It contains dark matter and dark energy, just very little normal matter. Standing on a planet in a galaxy inside the Boötes void would be an eerie experience. You'd look up at the night sky and see almost nothing. A handful of distant galaxies on the horizon, but no nearby neighbors, no grand spiral arms sweeping across the sky. You'd be isolated, cosmically alone, surrounded by hundreds of millions of light-years of emptiness in every direction. Intelligent beings in such a place might develop a very different cosmology. They might think the universe is much emptier, much lonelier than we do. Contrast that with being in the Virgo supercluster, which is where we live. We're part of a complex hierarchy of structures. Our solar system orbits within the Milky Way galaxy. The Milky Way is part of the Local Group, a collection of about 80 galaxies dominated by us and the Andromeda Galaxy. The Local Group is part of the Virgo supercluster, which contains about 100 galaxy groups and clusters spanning about 110 million light-years. And even that is part of something larger, the Laniakea supercluster, a gravitationally bound structure containing about 100,000 galaxies across 520 million light-years. Laniakea, Hawaiian for immense heaven, was only mapped in 2014 using measurements of galaxy motions. Galaxies aren't just moving away from us due to expansion, they're also moving toward or away from each other due to gravity. By mapping these peculiar velocities, astronomers traced the flow of galaxies toward gravitational attractors, revealing the large-scale structure of the cosmic web. We're all flowing toward something called the Great Attractor, a gravitational anomaly hidden behind the plane of the Milky Way. But wait, there's something even bigger pulling on us. The Shapley supercluster, the largest concentration of galaxies in the nearby universe, 650 million light-years away. It contains over 8,000 large galaxies with a total mass over 10 million billion times that of the Sun. Its gravity is so immense that it's affecting the motion of our entire supercluster, pulling us in its direction at about 600 kilometers per second. These structures are the largest gravitationally bound systems in the universe. Beyond this scale, expansion wins out over gravity. Structure doesn't form because space is expanding faster than gravity can pull things together. The cosmic web of filaments and voids represents the limit of what gravity can create in an expanding universe. It's a frozen snapshot of the density fluctuations present in the early universe, amplified by billions of years of gravitational growth. Now let's talk about something that challenges everything we think we know about the edge of the universe. What if space-time itself is quantized? What if, at the smallest scales, space isn't smooth and continuous but discrete, made of tiny indivisible units? This is the realm of quantum gravity, where general relativity meets quantum mechanics, and where our understanding of reality completely breaks down. The Planck length, about 10 to the negative 35 meters, is thought to be the smallest meaningful distance in the universe. Below this scale, quantum fluctuations in spacetime become so violent that our current theories stop making sense. Space and time themselves might be emergent properties arising from something more fundamental, some quantum substrate we haven't discovered yet. At the Planck scale, the universe might be a seething foam of virtual particles and quantum geometry, constantly fluctuating, creating and destroying tiny wormholes, baby universes, quantum tangles that exist for impossibly brief moments before dissolving back into the void. If spacetime is quantized, then zooming in far enough would eventually reveal the pixels of reality, the fundamental units that make up the fabric of existence. It's like how a smooth photograph dissolves into individual pixels when you zoom in close enough. The universe might have a resolution limit, a smallest possible scale, and asking what happens below that scale would be like asking what's smaller than the smallest thing. The question doesn't make sense. This has profound implications for black holes. At the center of every black hole, general relativity predicts a singularity, a point of infinite density where the laws of physics break down. But if spacetime is quantized, there might be no singularity. Instead, at the Planck scale, quantum effects might halt the collapse, creating something new, a Planck star, a bounce that could potentially spawn a new universe on the other side, or some exotic quantum state we haven't imagined yet. Loop quantum gravity, one approach to quantum gravity, suggests that black holes might be like atoms. They might have discrete quantum states, and they might tunnel from one state to another. When a black hole evaporates through Hawking radiation, instead of disappearing entirely, it might leave behind a tiny remnant, a Planck-scale object containing all the information that fell into the black hole, preserved in quantum form. This is important because it could solve the black hole information paradox. Information that crosses the event horizon isn't destroyed. It's encoded in the quantum state of the remnant. When the black hole finally evaporates, the information is released back into the universe. It's scrambled beyond recognition, encrypted in the radiation, but it's not lost. The universe doesn't delete information after all. The laws of quantum mechanics remain intact. String theory offers a different perspective. In this framework, fundamental particles aren't point-like objects. They're tiny vibrating strings of energy. Different vibration patterns correspond to different particles. An electron, a quark, a photon. Space itself might have extra dimensions beyond the three we experience. Dimensions curled up so small we can't detect them directly. These extra dimensions could be responsible for gravity's weakness compared to other forces. Gravity leaks into the extra dimensions, spreading its influence across higher dimensional space, which is why it feels weaker to us living in three spatial dimensions. If string theory is correct, then what we perceive as the edge of our universe might just be a boundary in the three dimensions we can access, while other dimensions extend beyond it. Our universe could be a three-dimensional membrane, a brain, floating in a higher dimensional space called the bulk. Other brains might exist parallel to ours, entire universes just millimeters away in a dimension we can't access. When brains collide, they might create big bangs, spawning new universes in a cyclic process that's been happening forever. These ideas are speculative, yes, but they're grounded in serious mathematics and serious physics. They're attempts to push beyond the limits of our current understanding, to explore what lies at the ultimate edge, not just the edge of the observable universe, but the edge of physical law itself, the boundary between what we can know and what might be forever unknowable. Let's bring it back to observations we can actually make. One of the most powerful tools for studying the universe's large-scale structure is gravitational lensing. When light from a distant galaxy passes near a massive object, another galaxy, a cluster of galaxies, even dark matter, the massive object's gravity bends spacetime, acting like a lens that focuses and distorts the background light. We see multiple images of the same galaxy, stretched into arcs and rings, magnified by the cosmic lens. The Hubble Space Telescope has captured stunning examples of gravitational lensing, where entire galaxy clusters act as natural telescopes, magnifying galaxies that would otherwise be too faint to detect. These lensed galaxies are some of the most distant objects ever observed, their light magnified by factors of 10 or even 100, allowing us to study them in detail despite their incredible remoteness. Gravitational lensing reveals dark matter. When we map the lensing effects of a galaxy cluster, we can reconstruct the distribution of mass, both visible and invisible. The results show conclusively that most of the mass is not in galaxies or gas, but in vast halos of dark matter surrounding and permeating the cluster. Dark matter makes up the scaffolding of the universe, the invisible framework on which galaxies are built. In August 2017, we witnessed something extraordinary. The collision of two neutron stars 130 million light-years away. LIGO detected the gravitational waves first, ripples in spacetime from the merger. Then, about 2 seconds later, the Fermi Gamma Ray Space Telescope detected a burst of gamma rays. Then telescopes around the world swung into action, observing the afterglow across the entire electromagnetic spectrum, from radio waves to visible light to X-rays. It was the most comprehensively observed astronomical event in history. That collision produced gravitational waves that traveled through space for 130 million years before reaching Earth. During their journey, they passed through expanding space, through the cosmic web, through voids and galaxy clusters, carrying information about the curvature of spacetime itself. By comparing the arrival time of the gravitational waves to the light, physicists confirmed that gravity travels at the speed of light, exactly as Einstein predicted. But here's what's fascinating. Those neutron stars produced heavy elements, gold, platinum, uranium, in a process called rapid neutron capture. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors. Much of it came from neutron star collisions billions of years ago. When those stars merge, they create a kilonova, an explosion that forges heavy elements and scatters them into space. Over billions of years, that enriched material gets incorporated into new stars, new planets, new worlds. You're wearing pieces of neutron star collisions. The atoms in your rings and watches are the remains of catastrophic events that happened before the Earth even existed, in galaxies far away. Those atoms traveled through space, got incorporated into the cloud that formed our solar system, condensed into our planet, got mined from the ground, and ended up on your finger. Every heavy element tells the story of cosmic violence and creation. Now, here's something that'll make you rethink everything about measurements. When physicists study the cosmic microwave background radiation, they're looking at patterns imprinted on the sky when the universe was just 380,000 years old. But hidden in those patterns is something remarkable: baryon acoustic oscillations. Before the universe became transparent, pressure waves, essentially sound waves, rippled through the hot plasma of the early cosmos. These waves propagated outward from overdense regions until the moment atoms formed and the pressure supporting the waves disappeared. They froze in place, creating a characteristic scale, a preferred separation between galaxies of about 490 million light-years. We can see this scale in the distribution of galaxies today. When we map millions of galaxies and measure how they cluster, we find they're slightly more likely to be separated by this specific distance than by other distances. It's like the entire universe is ringing like a bell, and we're detecting the harmonics billions of years after the sound stopped. This standard ruler allows us to measure cosmic expansion with incredible precision. By comparing how large this scale appears at different distances, different times in cosmic history, we can track exactly how fast the universe has been expanding at each epoch. The Sloan Digital Sky Survey has mapped over 3 million galaxies, creating the most detailed three-dimensional map of the universe ever made. The Baryon Oscillation Spectroscopic Survey, BOSS, part of that effort, measured the positions and distances of 1.5 million galaxies specifically to detect baryon acoustic oscillations. The Dark Energy Spectroscopic Instrument, DESI, is now measuring tens of millions of galaxies, pushing the precision even further. These surveys are answering fundamental questions. Is dark energy constant or changing? Is Einstein's general relativity the correct theory of gravity on cosmic scales? So far, the answer is Einstein was right. Again, the data fits his equations remarkably well. But the measurements keep getting better, and physicists are waiting, hoping, for the moment when the data deviates from Einstein's predictions, because that would point toward new physics, toward a deeper understanding of gravity and spacetime. Let's talk about what the universe looked like in its childhood, after the cosmic microwave background but before the first stars. This period, called the Cosmic Dark Ages, lasted for about 100 million years. The universe was filled with neutral hydrogen gas, cooling as it expanded, with no stars to light it up. It was truly dark, the only illumination coming from the fading afterglow of the Big Bang, redshifted into invisibility. During this time, gravity was working, pulling gas into denser and denser clumps, setting the stage for the first stars. Then came the cosmic dawn. In pockets where gas had accumulated to sufficient density, it collapsed under its own gravity, heating up until nuclear fusion ignited. The first stars were born, and they were monsters. Population 3 stars, as astronomers call them, were likely hundreds of times more massive than the Sun, burning through their fuel in just a few million years before exploding as supernovae. These stars had no heavy elements in them. They formed from pure hydrogen and helium left over from the Big Bang. Every atom of carbon, oxygen, nitrogen, iron, all the stuff that makes up planets and people, came later, forged in the cores of these primordial giants. We've never seen a population 3 star. They existed too early, too far away, and they lived too briefly. But their effects persist. They ionized the surrounding gas, carved out bubbles of transparency in the neutral hydrogen fog, and seeded the universe with the first heavy elements. Over millions of years, these ionized bubbles grew and merged until the entire universe became ionized again, a process called reionization. By about 1 billion years after the Big Bang, reionization was complete. The cosmic dark ages were over. The James Webb Space Telescope is searching for evidence of these first stars, looking for the telltale signs of their existence in the spectra of early galaxies. Some of the distant galaxies Webb has observed might contain population 3 stars or their immediate descendants. Finding direct evidence would be revolutionary, confirming our understanding of how the universe evolved from simple to complex, from primordial gas to the rich tapestry of elements we see today. But stars weren't the only things forming in the early universe. Somehow, impossibly quickly, supermassive black holes appeared. We found quasars, extremely luminous objects powered by supermassive black holes, dating back to when the universe was less than 700 million years old. These black holes have masses equivalent to hundreds of millions of suns. How did they grow so large so fast? Black holes grow by accreting matter, pulling in gas and dust and occasional stars. But there's a limit to how fast they can grow, called the Eddington limit. When material falls toward a black hole, it heats up and emits radiation. That radiation pushes outward, counteracting gravity. If the radiation pressure becomes too strong, it blows away the infalling material, shutting off the black hole's food supply. The Eddington limit sets a maximum growth rate based on the black hole's mass. Starting from stellar mass black holes, dozens of times the mass of the Sun, it should take billions of years to grow to supermassive scales if you're limited by the Eddington rate. Yet we find billion solar mass black holes when the universe was barely 500 million years old. They shouldn't exist. Either they started much larger, maybe there were intermediate mass black holes left over from the first stars, or maybe some black holes formed directly from collapsing gas clouds without going through a stellar phase, or they somehow grew faster than the Eddington limit, perhaps by accreting matter in ways we don't understand. This is an active area of research. Recent simulations suggest that dense gas in the early universe might have collapsed directly into black holes with masses of 10,000 to 100,000 suns, bypassing the stellar phase entirely. These seeds could then grow through rapid accretion and mergers, reaching supermassive scales in time to power the quasars we observe. But we're not certain. The early universe keeps surprising us. Quasars themselves are fascinating objects. They're the brightest sustained sources of light in the universe, powered by matter spiraling into supermassive black holes at the centers of galaxies. As material falls inward, it forms an accretion disk, heating to millions of degrees and radiating across the entire electromagnetic spectrum. Some quasars outshine their entire host galaxies by factors of 1,000 or more. A single quasar can emit the energy of 1 trillion suns. The most distant quasar we found has a redshift of 7.6, meaning we're seeing it as it was when the universe was just 670 million years old. That light has been traveling toward us for over 13 billion years. During its journey, it's passed through the entire history of cosmic evolution, through reionization, through the formation of the first galaxies, through the assembly of the cosmic web. Every photon carries information about the regions of space it traversed, absorbed and re-emitted by intervening gas clouds, each absorption line telling us about the composition and velocity of intergalactic material at different epochs. This is the Lyman alpha forest, a series of absorption lines in quasar spectra created by neutral hydrogen in the intergalactic medium. By studying these forests, we can map the distribution of gas throughout cosmic history, trace the reionization process, and measure the density and temperature of the universe at different times. It's like cosmic archaeology using light to excavate the past. Speaking of archaeology, let's discuss one of the most ambitious scientific endeavors ever undertaken: mapping the entire sky in multiple wavelengths simultaneously. The Planck satellite, launched in 2009, spent 4 years measuring the cosmic microwave background with unprecedented precision. Its maps show temperature fluctuations of 1 part in 100,000, revealing the quantum seeds that grew into galaxies and superclusters. Planck's data confirmed many predictions of cosmological models, but it also deepened some mysteries. The Hubble tension I mentioned earlier? Planck's measurements make it worse. Planck says the universe should be expanding more slowly than direct measurements indicate. Either systematic errors are affecting one or both measurements, or our cosmological model is incomplete. Maybe dark energy isn't constant. Maybe neutrinos have more mass than we thought. Maybe there's additional radiation we haven't detected. Maybe gravity works differently on large scales. The European Space Agency's Euclid mission, launched in 2023, is tackling this problem from a different angle. Euclid is mapping the three-dimensional distribution of 2 billion galaxies across 10 billion years of cosmic history, measuring how structure has grown over time. By comparing observations to predictions from different cosmological models, Euclid will constrain the nature of dark energy and test general relativity on cosmic scales. If dark energy is changing with time, Euclid will detect it. If gravity deviates from Einstein's predictions, Euclid will see that too. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will complement these efforts. Roman will conduct wide-field surveys in infrared light, studying dark energy through multiple techniques simultaneously: supernovae, weak gravitational lensing, baryon acoustic oscillations, and galaxy clustering. Having multiple independent measurements is crucial because it allows us to cross-check results and identify systematic errors. When different methods agree, we gain confidence. When they disagree, we know something interesting is happening. Let's zoom in on something happening much closer to home, but with implications for the edge of the universe: cosmic rays. These are high-energy particles, mostly protons, that bombard Earth from all directions. Some have energies exceeding anything we can produce in particle accelerators. Energies so high they shouldn't be possible according to our understanding of astrophysics. Where do they come from? Lower energy cosmic rays, up to about 10 to the 15 electron volts, likely come from supernova remnants in our galaxy. The shock waves from exploding stars accelerate particles to enormous energies, flinging them into space. But the highest energy cosmic rays, the ultra-high energy ones above 10 to the 19 electron volts, must come from beyond our galaxy. They're so energetic that not even supernova remnants can explain them. We need something more powerful, maybe active galactic nuclei, maybe gamma-ray bursts, maybe colliding galaxies, or maybe something we haven't thought of yet. There's a catch, though. Ultra-high-energy cosmic rays interact with the cosmic microwave background. When a proton with sufficient energy collides with a microwave photon, it can produce pions, draining energy from the proton. This process, called the GZK cutoff after the physicists who predicted it, limits how far ultra-high-energy cosmic rays can travel. Any proton above the GZK threshold can only come from within about 160 million light-years. Beyond that distance, it would lose energy to microwave photons and arrive at Earth below the threshold. We've detected cosmic rays above the GZK cutoff. Not many, but enough to confirm they exist. This means their sources must be relatively nearby, within our cosmic neighborhood. but we haven't definitively identified those sources. We know the general direction some of these particles come from, but not the exact objects producing them. It's one of the great unsolved mysteries in astrophysics. Something nearby is accelerating particles to energies we can barely imagine, and we don't know what it is. The Pierre Auger Observatory in Argentina, covering an area larger than Rhode Island, detects ultra-high-energy cosmic rays by observing the showers of particles they create when they hit Earth's atmosphere. A single incoming proton can generate billions of secondary particles cascading through the atmosphere. By detecting these showers with an array of ground sensors and fluorescence telescopes, physicists can reconstruct the energy and direction of the original particle. One cosmic ray detected by the Fly's Eye Observatory in 1991 had an energy of about 320 million trillion electron volts, equivalent to a baseball traveling 60 miles per hour, except all that energy was concentrated in a single subatomic particle. It's called the Oh My God particle, and to this day, we don't know what could have accelerated it to that energy. It came from the direction of Ursa Major, but there's nothing obvious in that part of the sky that could produce such a particle. It remains a cosmic enigma. These ultra-high-energy particles are probes of physics at energy scales we'll never reach in laboratories. They're natural particle accelerators, and studying them gives us insights into fundamental physics. If cosmic rays can travel from the edge of our cosmic neighborhood, they carry information about magnetic fields, intergalactic gas, and the sources that produce them. They're messengers from the outer reaches of the observable universe. Now let's talk about something that pervades all of space but that we rarely consider: magnetic fields. The universe is threaded with magnetism. Stars have magnetic fields. Galaxies have magnetic fields spiraling through their disks and extending into their halos. Galaxy clusters have magnetic fields permeating the space between galaxies. Even the intergalactic medium, the near-empty space between galaxy clusters, has weak magnetic fields. Where do these fields come from? Some might be primordial, dating back to the very early universe. Others are generated by dynamos, moving electrically conducting fluids that amplify seed magnetic fields. In stars, convection and rotation drive dynamos that create and maintain stellar magnetic fields. In galaxies, turbulence and differential rotation do the same on much larger scales. The Sun's magnetic field flips every 11 years. The Milky Way's magnetic field is much more stable, but it's constantly being shaped by supernova explosions, stellar winds, and the motion of gas clouds. Magnetic fields affect cosmic structure formation. They provide pressure support against gravitational collapse. They channel the flow of gas in galaxy clusters. They accelerate cosmic rays and confine them to regions of space. They produce synchrotron radiation when electrons spiral along field lines at relativistic speeds. Radio telescopes can map magnetic fields across galaxies and clusters by detecting this synchrotron emission and measuring how it's polarized. The Square Kilometre Array, when complete, will revolutionize our understanding of cosmic magnetism. SKA will map magnetic fields throughout cosmic history, from the present day back to the epoch of reionization. By understanding how magnetic fields evolved, we'll gain insights into galaxy formation, cosmic ray propagation, and the physics of the intergalactic medium. Magnetism is a fundamental but often overlooked aspect of cosmic structure, and we're only beginning to understand its role in shaping the universe. Here's a question that sounds simple but cuts to the heart of cosmology. Why is there something rather than nothing? After the Big Bang, matter and antimatter should have been created in equal amounts. When matter and antimatter meet, they annihilate, converting into pure energy. If the early universe had equal amounts of both, everything should have annihilated, leaving only radiation. Yet here we are, made of matter, living on a planet made of matter, in a galaxy made of matter. Where did all the antimatter go? There must have been a slight asymmetry, a tiny imbalance favoring matter over antimatter, about one extra matter particle for every billion matter-antimatter pairs. When annihilation finished, that tiny excess remained, and that's what makes up everything we see today. Every atom in your body exists because of this asymmetry. Without it, the universe would be empty radiation. No stars, no planets, no life, no consciousness. Understanding why this asymmetry exists requires physics beyond the standard model of particle physics. The standard model can't explain enough asymmetry to account for the matter we observe. There must be additional processes, perhaps involving heavy particles that existed in the early universe but have since decayed, or perhaps related to the Higgs field or neutrinos. Experiments at the Large Hadron Collider and other facilities are searching for clues, looking for subtle differences in how matter and antimatter behave that could explain the cosmic imbalance. This is one example of how cosmology and particle physics are intertwined. The largest scales and the smallest scales inform each other. To understand the universe as a whole, we need to understand its fundamental constituents. To understand fundamental particles, we need to study them in the extreme conditions of the early universe, conditions we can't reproduce in laboratories. Consider neutrinos, ghostly particles that barely interact with anything. Trillions of them pass through your body every second, mostly from the sun, and you don't notice. Neutrinos are created in nuclear reactions, in supernova explosions, in cosmic ray collisions, and in the Big Bang itself. The universe is filled with relic neutrinos left over from the Big Bang, a cosmic neutrino background analogous to the cosmic microwave background. These neutrinos have been traveling freely since the universe was about 1 second old, even earlier than the release of the microwave background. We've never detected cosmic neutrinos directly. They're too low energy, too weakly interacting. But we know they're there, and they affect the evolution of cosmic structure. Neutrinos have mass, though we don't know exactly how much. Their mass influences how structure forms because massive particles resist being pulled into dense regions by gravity. By measuring the clustering of galaxies on large scales, cosmologists can constrain the total mass of neutrinos. Current data suggests the sum of neutrino masses is less than about 0.1 electron volts, roughly a millionth the mass of an electron. This might seem insignificant, but neutrinos are so abundant that even this tiny mass makes them a significant component of the universe's total mass energy budget. They're a form of hot dark matter, moving at relativistic speeds in the early universe. Hot dark matter doesn't cluster well, smoothing out small-scale structure. The fact that we see structure on small scales tells us most dark matter must be cold, moving slowly, allowing it to clump efficiently. But neutrinos still matter, and future surveys like DESI and Euclid will measure their mass more precisely, revealing another piece of the cosmic puzzle. Let's talk about time again, but differently. The universe is 13.8 billion years old, but not all regions of the universe have experienced the same amount of time. Because of relativity, time passes differently depending on gravity and motion. Clocks near massive objects tick more slowly than clocks far from mass. This means regions of the universe with different matter densities have experienced slightly different amounts of proper time since the Big Bang. These differences are tiny, but they accumulate over cosmic history. A clock sitting in a galaxy cluster, surrounded by mass, has experienced slightly less time than a clock floating in a cosmic void, far from any massive structures. When we talk about the age of the universe, we're talking about the time experienced by an observer moving with the cosmic expansion, far from any concentrations of matter, a fundamental observer. But real observers, living in galaxies and clusters, experience slightly less cosmic time.